All right, so it's my pleasure to welcome everyone again at our One World IAMP seminar in mathematical physics. And it's my pleasure to introduce our next speaker, Julian Sonner, who's going to talk about random matrices and black holes, new connections from holography. And this talk is being recorded, and you can watch the video of this talk and other talks online on our YouTube channel. So Julian, please go ahead. The floor is yours.
All right. Thanks, Kasia. Thanks to all the other organizers for inviting me to speak at the seminar. I'm very excited to speak to this audience. I don't think I know so many of you, so it's wonderful to introduce my work to you and hopefully discuss it. So I will start this seminar a little bit colloquium style because I believe that not everyone is familiar with this holographic duality or ADS-CFT duality. If the level is, let's say, too lowbrow, I apologize for everyone I'm offending with this, but maybe it's worthwhile going through it anyway. And then during the second part of my talk, I will go into more recent material, also my work in particular on this connection between random matrices, quantum chaos, and black holes. So that work is based on a series of papers with a set of wonderful collaborators, and I would like to mention them. But as I said, that concerns mostly the second part of the talk. But so this is work with Alexander Altland, who actually is a world expert on quantum chaos and related aspects from Cologne, with my postdoc Pranjal Nayak and my former graduate student Manuel Bielma, as well as with postdoc Alex Belin at CERN and with Jan de Boer, who is faculty in Amsterdam. And so, yeah, roughly speaking, this is a series of papers which talk about spectral issues, about operator ergodicity, and more specifically about conformal field theories, if we get there, and operator product expansion coefficients. But let's take a step or many steps back without talking about current research, and let's talk about sort of the basic idea of what is this ADS-CFT duality, or holography, as I prefer to call it. Oh, and of course, it goes without saying that I invite questions at any point. So please don't be shy to ask clarifying questions. So, well, I still would like to motivate the reason why we work on this specific set of topics within holography with one slide. So the physical, or let's say theoretical physical motivation for this is this old puzzle, which is the fact that quantum mechanics, which is, as we know it, a unitary theory, and gravitational physics seem to have some conflict about precisely this issue of unitarity. So examples that have been quoted, potential conflicts that have been highlighted, concern what people refer to as a black hole information problem, as was raised by Stephen Hawking, but which was made very precise in what is called the Page curve. So the Page curve is basically a proposal of how the entropy of a black hole, evaporating black hole, should behave in a unitary theory, and it contrasts this to Hawking's prediction of how it seems to behave according to his calculation in semi-classical gravity. We will get back, of course, to this more precisely in the second part of the talk. But one can make similar observations actually about, let's say, more down-to-earth observables. So in fact, one can make similar observables about this perceived or supposed lack of unitarity, about the long-time behavior of other observables, things that are as simple to state as two-point correlation functions of certain fields. And that's in particular the context that we will address. Now, these paradoxes, they come actually from the fact that for a long time, we've been attempting to interpret black holes as thermodynamic entities, which was, of course, first suggested by Wittgenstein and made much more precise by Hawking. Now, here is where my interest in this ADS-CFT as a tool to study gravity comes in. So I would like to, as I will introduce, use this duality to use a reformulation of gravitational dynamics to make some more precise statements and hopefully some progress on these long-standing issues. So within ADS-CFT, one can basically formulate the idea of a black hole that forms from a pure state very precisely. And I have graphically visualized here. This is just supposed to be a motivation, but it does actually stand for a calculation that we did many years back. So what one can do is, as you will see, the idea of this ADS-CFT is that you define observables that are at the boundary of some volume of space-time. So the boundary here would be the mantle of the cylinder, and the space-time would be the infilling part of the cylinder. And we can define some very well-defined initial states in a quantum field theory that lead to the contraction of a distribution of matter, which will then lead to horizon formation and singularity formation, in other words, black hole formation. And the idea of how does this thermal state of the black hole arise, hopefully in a unitary fashion, is then actually translated into a question which in some sense is much less mysterious. Namely, the idea of studying the thermalization dynamics of a non-equilibrium initial state in a strongly coupled quantum field theory. And so this leads to conceptually investigate the ideas of quantum chaos and quantum ergodicity in the context of this holographic duality. So this is the main motivation. So I will now go to explaining a little bit more this terminology of boundary and bulk and so on and so forth. And then I will move on to pulling these things in the direction of quantum chaos and quantum ergodicity. And I believe that many of you actually know this somewhat well or very well. This is how you can see that these random matrices and random matrix theory will make its entrance. It has to do with ergodic behavior of quantum systems. Okay, so let me state what this ADS-CFT duality is supposed to be. So as we are all familiar, dualities are actually found in many areas of physics and mathematics. And they basically mean that you can have one and the same physical phenomena. So, for example, one quite common occurrence is what is known as particle-vortex duality in condensed matter physics. So let's talk about, for example, some basic notion like conductivity of a piece of a material. And there are two different many-body descriptions that lead to exactly the same predictions in terms of all of the possible correlation functions and associated physical phenomena that you can associate with them. So one description talks about elementary excitations, perturbative excitations like electrons and particles. And then there is an equivalent formulation in which the basic objects are instead objects that you would more call like vortices, like magnetic vortices in the system, which are more like solitons. And the description in terms of the particles and solitons are dual to each other in the sense that they apply in different regimes of parameters, but where they overlap can be shown to give exactly the same physical predictions. The only thing that's left to do in some sense, well, you might want to rigorously prove such dualities, but the only thing that's left to do before that is to formulate a sort of a dictionary that tells you how do you formulate physical questions in one framework and how do you formulate them in another framework. But what I want to emphasize is that the kind of duality which we'll be talking about, namely ADS-CFT, is special among the set of dualities because it involves gravitational physics. And so in the most general sense, what it means is that it's actually a duality. So we're talking about the same physical content, but it can be formulated either by talking about quantum gravity in asymptotically anti-de Sitter space, whatever that is, more about this in a minute. Or we can talk about it in terms of something much more familiar, namely quantum field theory, so specific quantum field theories, but on a fixed background, meaning that the thing that is actually dynamical here on the left, namely the background itself, the metric, is kept fixed here, and the dynamical object in some sense seems to make absolutely no reference to gravitational degrees of freedom. Yet the statement is that whatever question you can ask about objects that are natively in this quantum gravity world, you can formulate in a different way using this dictionary to be specified, and ask the corresponding question about the quantum field theory, and of course, vice versa. So, however, what are these main players here? So ADS, well, it stands indeed for anti-de Sitter space. It is the maximally symmetric geometry, and let me define it in d+1 spacetime dimensions. So it's the maximally symmetric pseudo-Riemannian manifold with constant negative curvature in d+1 dimensions. And because, you know, if you talked about the one with positive curvature, you would call it de Sitter space. You have now anti-de Sitter space. You reverse the curvature. In 2 dimensions, this is actually easily specified. It's essentially a Lorentzian version of hyperbolic space. So here I'm visualizing this by showing you the hyperbolic disk. So this is the disk with the hyperbolic metric on it. And this hyperbolic metric is nicely illustrated here by Escher by showing, you know, these constant area surfaces and tiling it by a duality between angels and demons. This is also some sort of you know, artistic representation of duality. But the point is that we want to study gravity on these kind of surfaces, which means that the geometry is dynamical, in which we mean that we can have locally fluctuations of this geometry, which are actually going to be described by essentially the Einstein-Hilbert term, or the, you know, the Einstein-Hilbert action. But I'm saying essentially the Einstein-Hilbert action because we actually, in this framework, will be able to go beyond the classical approximation. And we will actually be able to describe quantum fluctuations. So in other words, these geometrical fluctuations of this asymptotically anti-de Sitter space, we will be able to go beyond general relativistic description of this space-time. And now let me just make one observation that in the general, sorry, there, I look at the chat. The slides, okay, excuse me. The isometries of this maximally symmetric geometry, so the group of geometric symmetries can actually be shown to satisfy the Lie algebra of SO2, D. So if you write down all of the geometric isometries, the generators, and you calculate their Lie brackets, you get precisely the Lie algebra of SO2, D. So I just want to notice that because I will come back to that in a second. Because the next question is, of course, what is CFT? Well, in this case, we're talking about a conformal field theory. And so we're going to talk about a quantum field theory in D dimensions to be contrasted with these D+1 dimensions, which are equipped with a large symmetry, so-called conformal symmetry. And so these are, in flat space, these are transformations where I send coordinates x to a new set of coordinates x primed, such that the metric is preserved up to a positive factor omega squared. And if you ask what is the set of all transformations that act on the metric like this, what you get is precisely the same. Well, I talked at the level of the algebra, so the generators again of these transformations will form the Lie algebra SO2, D. And so I just wanted to highlight this because this is in some sense the first entry in this dictionary. So there is going to be on either side a role for this one object, this one idea SO2, D, but it has 2 entirely different incarnations. On one side, on the dictionary, so in the ADS language, we call them ADS isometries, so the geometric isometries of this space. And on the other side, the same structure is going to be the conformal symmetry. So, right. So why do we call this sometimes the holographic principle? So here again, you know, all of this is quite a general level. So let me just proceed a little bit at that general level. So now we've shown that this is sort of a duality between, or that is supposed to be a duality between ADS space and a conformal field theory, but actually there is some more physical concept behind this, which is realized in this as duality. And this is what's called the holographic principle. So this goes back to the idea that is indeed due to Wittgenstein and Hawking, namely that the entropy of a black hole, generally speaking, which is also true of black holes in ADS, is proportional to the area of the event horizon in units 4 times g Newton, and not to the volume. So in some sense, the number of degrees of freedom that give rise to black holes, they are extensive with the surface and not the volume of this object. And it has been suggested over the years, for example, by people like 't Hooft and Susskind, that this should be a general property of gravitational theories, namely that in some sense, the amount of information should be surface extensive. And then one can sort of make this bold generalization that in fact, there should be fully a theory that only is localized on the surface of a given volume of space-time, which fully accounts for the physics on the inside of this volume. Now, this idea was never made very concrete up until the advent of this ADS-CFT duality. And I just want to point out that ADS-CFT duality is a precise implementation of this idea, because the ADS theory, we've already insisted on it, was in d+1 dimensions, whereas the CFT was only in d dimensions. And the geometric relationship is that indeed the interior, so here I'm visualizing it 2 dimensions, the interior of this disk being the volume is where gravity lives. And this dual theory, the CFT, it actually lives on the boundary. So this boundary here is 1 dimension lower, and then therefore encodes like a hologram, higher dimensional information on a lower dimensional surface. And why do I make such a big deal of this? It's because, in fact, our understanding nowadays is that the duality that started as ADS-CFT actually goes beyond just ADS and beyond just conformal field theories. So you can deform the ADS space and you can deform the conformal field theories to the extent that you don't even talk about conformal field theories anymore. You can have actually field theories that have a non-trivial renormalization group flow and still preserve this idea of the holographic duality. So in some sense, the essence is this holography. But its most well understood and purest incarnation is the duality between pure ADS and pure CFTs. Okay, so a little bit more on this general overview. So we have seen one entry in this dictionary. We have seen that somehow what is a geometric isometry on one side becomes a conformal symmetry on the other side, but we're really talking about the same idea. Now, there are other elements of this dictionary. I would like just to mention a few. So for example, when you talk about the gravitational description, you might want to talk about the idea of a metric, or even if you want diffeomorphism invariant quantities that characterize the curvature, like, you know, Ricci scalar or powers of the Riemann tensor or whatever. Those things, so if you want to talk about correlation functions of those objects, what you're talking about in this conformal field theory is going to be correlation functions of the energy momentum mode of this conformal field theory. So in other words, if I wanted to know the endpoint correlation function of space-time curvature, and I wanted to compute it from my quantum field theory, I would look at some well-defined endpoint correlation functions of energy momentum. And so, for example, the ripples, so the small perturbations of the metric that can propagate like gravitational waves, they actually are simply the correlation functions of this conformal field theory. And what is the object that those two things encode? Well, of course, there is the generating functional of all correlation functions. And there is a way of computing it from simply gravitational data. And you will see in the second part of my talk one example of this. And there is a way of calculating it from the conformal field theory side. And then finally, this entry here, I'm mentioning this because I think this illustrates a little bit also, let's say, a very appealing, powerful feature of these dualities. Namely, that sometimes things that are very obscure, or at least appear to be very obscure and perhaps difficult to address on one side, become very beautiful, simple objects on the other side, and make therefore also this dual mapping quite useful. And one such notion is entanglement, or rather the entanglement entropy, let's say, of subregions of this conformal field theory. And this is in a well-defined way mapped to the problem of just finding extremal surfaces in these geometries. So a very simple geometric problem, which basically boils down to solving partial differential equations, which is, you know, a well-defined problem, and is related to the, well, at least technically, really rather complicated idea of entanglement entropy in quantum field theories. And just to illustrate that, I sometimes make this joke about a linguistic analogy of these dualities. You can have, you know, two different languages that actually refer to the same object. And I always like this when I look at my Landau Lifshitz. I have a German translation. There is in the index actually the item Drehimpuls-Wahrscheinlichkeitsdichte-Verteilungsfunktion. I mean, you know, it's a simple concept, and I'm sure almost every other language has a simpler way of expressing it. And in the same way, in ADS-CFT, you can actually make this seemingly very complicated object, namely the entanglement entropy of a subregion, quite manageable. So let's, you see, our theory lives on this boundary. The object I'd like to compute is, let's us fix a subregion R. So in this case, it's just this interval. And let me ask, what is the von Neumann entropy of the reduced density matrix on R? So I trace over the Hilbert space of all the states that are localized in the complement of R. And I ask, what is the result of computing minus trace of this matrix, of this metric rho times log rho? So the von Neumann entropy of the reduced density matrix on R. Well, that's a formidable calculation. However, from this ADS-CFT perspective, and this was taught to us by Ryo and Takanagi, we can do the following very simple computation. We consider the space of all surfaces that are anchored at these boundary points of the interval R, and we choose the one that minimizes the distance. In this case, it's really the geodesic distance, because you just have a one-dimensional curve. In higher dimensions, this would be surface and volumes. And once you have found this minimal area, which, as I said, is just a problem in the calculus of variations, you take its area, you divide it by 4 times G Newton, and you get this same entanglement entropy. And well, I wanted to make one, so this is, in my opinion anyway, a very beautiful geometrization of a problem that isn't in any way obviously geometric if you think about it in terms of quantum field theory. And in many cases, it actually turns out to be a calculational simplification as well. But I wanted to point out that the fact that this actually takes a form is quite similar to the Bekenstein-Hawking entropy is not a coincidence. But
yeah, is this identity a conjecture or a theorem?
So in 3 dimensions, so in 3-dimensional ADS-CFT, it is proven, but it's not proven at the level of a mathematical theorem. In fact, almost nothing in this field is, if one is honest. But it is proven at the level of rigor of a theoretical physicist in 3-dimensional ADS. In higher dimensional ADS, there is no such even theoretical physics proof available, but a lot of non-trivial evidence that it is actually true.
Thank you.
Thank you. So is there like a reason why it cannot be made into a theorem in 3D, or is just sort of technical problem?
I think the reason why it will be hard to make into a theorem is that to prove anything at the level of a theorem, what you actually have ahead of you, what you're faced with is that you need to prove that calculating something in 3-dimensional quantum gravity gives the same result as calculating it in 2-dimensional CFT. In 2-dimensional CFT, we have very good handle on calculating entanglement entropy because you can use these operators, twist operator tricks and so on. But saying that you want to prove something rigorous about something that lives in 3-dimensional quantum gravity, I think that the whole theory is just not defined at the level of rigor that you can make a theorem out of it.
Right.
If you see what I mean. But if I just wanted to use the 2-dimensional CFT computation as the mathematical definition of 3-dimensional quantum gravity, then I'm done. But I think that's somehow not the point. That would be kind of a cheating.
It's cheating, but hey, okay.
So,
that makes sense. Thank you.
So what about 4-dimensional quantum gravity?
Even worse.
Okay. Okay.
I think that's an honest statement. So so now good. So let me go into more like topics of current research, and there we can probably also talk more about levels of rigor, because we're not talking about proving the grandest of theorems, but maybe just some sub aspect of it, which might be more manageable. But by the way, I mean, I should say that, of course, in terms of trying to do, I think trying to prove this ADS-CFT conjecture is a wonderful idea and may actually give rise to some very rich mathematical theories, simply because the ideas behind it seem to be so far-reaching. And there are people who work on this, and that in particular, again, in 3 dimensions, have recently made some interesting progress. But okay, that's not something that my talk is about, but just as a, just as an advertisement.
This was 3 Euclidean dimensions, or?
No, I think this can be related. No, so I'm talking about 2 + 1 space-time dimensions, and people do work with Lorentzian signature, but sometimes in order to make progress, I think they talk about the Euclidean version, so three-dimensional version of hyperbolic space, if you want. Okay.
Okay. Right.
So now, so both of these examples, namely the one that I mentioned first, page curve and correlation functions, have recently enjoyed some new progress. But as often, this progress also comes with new questions. And the most intriguing one, the one that I want to focus today, is what we refer to in the field right now as the role of the ensemble. And that means that gravity appears to contain these contributions, wormholes, I will derive those for you, which strongly suggest an average over an ensemble of quantum systems. So think about random matrix theory. This will actually be related to random matrix theory. And this has triggered essentially a bifurcation among practitioners, namely that you can have 2 attitudes. One part says that in some sense, this ensemble of quantum systems, so you don't have one quantum system, now you have to average over quantum systems, is actually a fundamental new, let's say, data point that we have in our understanding of gravity. Namely, it's really true. There is maybe one gravitational theory. We refer to them usually as the bulk theory. But the boundary description is due to many, many quantum systems. Think about random matrix theory. But the second point is the one that I want to argue for, is that in fact, this is not true, because it is in fact well understood how these random matrix or ensemble descriptions can arise in other contexts, namely disorder models and generally quantum chaotic physics. And what I want to argue for the remainder of my talk is that this is actually the right way to think about these contributions and the apparent role of the ensemble in this ADS-CFT duality. So let me try and get there. So let me just advertise what we did. Okay, so I like to quote this, well, which is actually the way that I quote it is actually the unofficial motto of Switzerland. I only learned this. So what I want to say is basically that one quantum system can behave like the average over many quantum systems, one for all, and all can behave like one quantum system. So in Latin, and as they say in Switzerland, unus pro omnibus, omnes pro uno. So the 3 musketeers, which basically, so I'm going to develop for you a framework that allows to understand this emergence of chaotic correlations using some universal quantum chaotic properties. So we develop this as an effective field theory, and we make this the consequence of a symmetry breaking principle, which we call causal symmetry breaking. And this will give us a version of an effective field theory description of quantum chaos. And I want to tell you the story both from the gravity perspective and from the quantum system perspective, and show you how this well resolves these apparent this apparently puzzling appearance of ensemble averages. So it will explain the role of these ensemble averages for individual quantum theories, and therefore explain this occurrence of wormholes. But it is also, in fact, nicely a technically very efficient tool to make specific quantitative predictions. So how random matrix theory actually applies to black holes, then how other ideas related to thermalization appear, namely something that goes in the name of eigenstate thermalization hypothesis. And well, I probably won't have to talk about it, but it also predicts something about the statistics of OPE coefficients. So let me start now by introducing the required notions of quantum chaos. Unless, of course, there are questions, by the way. Okay, so quantum chaos. So I want to draw your attention to a particular aspect. So let us ask the following question. For example, one can ask this in relatively simple chaotic systems, which can be quantized, such as quantum billiards, the Sinai billiards, non-integrable versions of it. So you put yourself onto one energy level. So select one energy eigenstate of this quantum billiards, or some other chaotic system, by the way. And you ask the question, let me scan through the spectrum and let's count how many other levels I encounter as I scan through the spectrum. Now, what you will get is something like this gray histogram here, which is my artistic impression of some potentially real, let's say, experimental data. Now, the question is, so S, by the way, is energy difference. So I start with one energy level and then I scan through. And so I map this as a function of energy difference in some convenient units where the maximum of this curve will be at 1. And the question is, what is actually this curve that is approached as I make my sampling steps infinitely small and I sample the spectrum with infinite precision? Well, the conjecture, which was first in a different context formulated by Wigner, but which I think is mostly associated with the names of Boigas, Giannoni, and Schmidt, is that this is actually well approximated by an average over Hermitian matrices, which are drawn from a probability distribution that depends only on some fundamental anti-unitary symmetries of the system. So the idea is that the energy levels, the correlations between energy levels in one given quantum system, so I fix the Hamiltonian, is actually well approximated by the average over quantum systems. So the energy levels follow some random matrix theory law. And what I've drawn here is the so-called Gaussian orthogonal ensemble, which was one of the ensembles defined by Wigner all the way back in the 50s. But the quantity that actually most makes contact to black holes is in fact the Fourier transform of this probability distribution of energy level distribution, gaps in the energy spectrum.
Excuse me, why GOE and not GUE?
I have just chosen here the GOE, but depending, so if the system has time reversal symmetry, then it will follow the GOE or the GSE. If it doesn't have that time reversal symmetry, then it will follow the GUE. And in this Sinai billiards case, the actually appropriate one is the GOE. But it's a very good question because in fact, what we will make contact with in gravity will be the GUE, the unitary ensemble. Thanks. So the Fourier transform of this two-level correlation will be something that essentially as a function of time measures finer and finer energy differences. And this will give you a curve, which I have also approximated here as a function of the logarithmic time and the log of this so-called Fourier transform, the Fourier transform of this level density, which I call K. And again, the idea is that at least, what I didn't say is that, this overlap here of these two curves, that occurs basically on the scale of a few average level spacings. So, the fine-grained spectrum is basically well approximated by these random matrices. And that in the time domain translates to the fact that the Fourier transform at late times starts approaching this purple curve, which is the one that would be predicted by a pure RMT average. And the timescale at which it starts being well approximated, so the real signal, the black one, starts being approximated well by the RMT description is called the tauless or ergodic time. And then, this other time scale here where it sort of saturates is often known as the plateau time. And it sort of scales as the size of the Hilbert space. So this S here is the entropy. And I want to basically discuss the importance of this linear rising feature and the plateau in ADS CFT. That is going to be my goal. And so let me give a preview of what's going to happen. Basically, you're going to have some early time dynamics, which is going to be described by what I would call semi-classical gravity. So these geometries, we will get to explaining them. Okay.
Excuse me, I missed. What is K of T?
Good. K of T is the Fourier transform of the two-level correlation function. Let me see if I can actually now annotate here on this iPad. Oh, no, I cannot now. Interesting. Can I annotate here? Yes. So in actual fact.
So what is the difference between R2 and K?
Yes, I'm going to say that in a second. So R2, sorry, I'm using my keypad, so this will not be the greatest graphically. So R2 is going to be rho of E, the density of levels at energy E, and the density of levels at energy E plus omega, let's say. So this is a correlation between two levels, okay? With respect to this eigenstate ensemble that I used also here. And K is basically the Fourier transform of this. So K is going to be R e to the I omega t, I omega t, integrated over omega, let's say. Okay, so it is basically Fourier transform with respect to the difference in energies. And that gives me a time-dependent quantity, but it encodes really the same physics as this two-level correlation function. And this two-level correlation function is actually this P of E, if I wrote this, sorry, P of omega would be the integral over all energy of R2. So it's in some sense once more averaged, okay? P is the thing that Wigner liked, R is the thing that we like more, but they're very related quantities.
Thank you.
Okay, so so let me continue. Can I stop? Yeah, good. So I will erase this now. So now, as I was saying, so roughly the story will be the following, is that, and we will have some early time phase, which is described by semi-classical gravity. So let's just say Einstein-Hilbert plus small corrections. Then this Thouless time actually defines a new phase in some sense in which this gravitational theory is, where you have new contributions, which are two boundary geometries that are connected. Don't worry, I will explain exactly what the point is of these geometries. But in some sense, it's a new phase that we now understand. And we have these correlations in the spectrum that are actually responsible for these features. They are precisely correlations between two regions of space-time, which we might call Euclidean wormholes. And this late time, very, very late time phase is still somewhat mysterious, and I hope maybe I can make some remarks on that too. So our goal is to calculate correlations in the spectral density. So we want to calculate this quantity here. I've distributed the omegas a little bit more symmetrically than I did just now, because well, I was writing with my index finger. But so we want to have the correlation of one energy level with an energy level that's one omega apart from it. And we want to do some averaging here in the sense that we either do the same as we did with the Sun A billiard. So we sample over with some sample size. This is what people sometimes refer to as the eigenstate ensemble. Or we could actually do some explicit averaging over a small set of parameters, like some coupling constants that you have. SYK, you can ignore this, but this is a particular set of models where you can average over coupling parameters. Or you could think about some other kind of coarse-graining procedures. So you might have some other reasons why, for example, you cannot determine with absolute certainty the energy, and so you have to do some smearing. So as I said, we will give such a calculation. So we will calculate this R2 from the boundary perspective and from the bulk perspective. And I would like to emphasize the role of universal spectral correlations. So universal in the sense that they are determined by only a small set of symmetries and don't depend on the microscopic parameters. So how do we do this? Now we get back to this idea of the dictionary. So in the bulk, a quantity that is very natural to calculate is the partition function at inverse temperature beta. And this goes all the way back to the slide where I showed the generating functional of correlation functions W of J. In fact, this generating functional of correlation functions is the partition function. That is one of the entries of the ADS-CFT dictionary. But we don't actually have to understand that now because I will show you another way of understanding what this partition function does. But of course, as we all know, we can write this as the Laplace transform of the density of states. Okay, this is just another way of writing the partition sum. So we can recover rho, the object that we're interested in, as the inverse Laplace transform of this object Z of beta that I just told you is natural in gravity. So what we are interested in calculating is this Z of beta. And I want to make reference to the same kind of averaging procedures that I introduced here. And I define it for the time being as the evaluation of the Z of beta within the gravitational theory. So Z of beta slash gravity means I use the gravitational side of this duality to calculate this object. But more generally, what we could actually ask would be, what happens if we calculate the analog of correlations of many of these rows, which would be calculating Z of beta 1 all the way up to Z of beta n, using our gravitational dictionary to do it. And sometimes to make this more obvious, this quantity I will also denote it as Z subscript n of beta 1 up to beta n. Now,
excuse me, what does it mean physically? You have beta 1, beta n, so you have several temperatures.
That's right.
In one system. So what does it mean? You have several thermal reservoirs, or?
Well, physically, I don't know. So what I would say is that if you take your energy density rho of E, you can define the Laplace transform with respect to beta as a parameter. Okay, and I can calculate at least this quantity formally for a different set of betas where all the different parameters in this Laplace transform of the several spectral density correlations are different.
Okay.
Formally, I can do it, but I have not thought about it as being coupled to different reservoirs. And I'm now a little bit puzzled why you say that, because, I mean, I understand why you say it, but it causes me some puzzlement, because you would expect that these things cannot necessarily be in equilibrium. But I do find solutions which would indicate equilibrium. So I can't give you a good answer right now, but I'll think about it a little bit. Maybe I'll come up with a better answer.
Thank you.
So, so there is a much celebrated result of Gibbons and Hawking from the late 70s. And that says that if you actually calculate formally, if you consider formally the path integral of a Euclidean matrix in what they called at the time Euclidean quantum gravity, this defines a thermal ensemble, and in particular, it defines a thermal ensemble at inverse temperature beta if you formally path integrate over Euclidean metrics such that the time direction is identified with period beta. So beta is this inverse temperature parameter here. So, well, let me first say introduce this graphical representation, and then let me say a few more words about it. So I will represent this graphically by showing the boundary, okay? The boundary shares the same time direction as the bulk, always in our story. And so I will indicate the boundary only by this time circle here. Of course, there may be other directions. But then what we're supposed to do is we're supposed to calculate over all possible Euclidean manifolds that have this same boundary, the boundary being the time circle here. Well, this path integral, and here you see this, for example, is one way of replying to Kasia. I mean, in a mathematical sense, I don't think anybody knows how to make sense of this kind of path integral. But what can be done in practice, it can be evaluated to one loop accuracy. So you can actually do a saddle point analysis of these kind of things, where the action here really is the action of Einstein-Hilbert with a negative cosmological constant. And then you will get, you know, the action will localize on the saddle points, which would be classical solutions of gravity, of Euclidean gravity. Plus, then you get a quadratic action for all the fluctuations around it. And that can be done by just using, you know, zeta function regularization or whatever you want. And it gives you sensible answers. But whether this object here as such has any good mathematical definition, at least to my knowledge, is so far beyond our capabilities, especially in higher dimensions, that, you know, they basically have no chance, I think, of making this particularly rigorous mathematically. But at the level of semi-classics, you close your eyes and you just do the one loop path integral. This actually makes sense. And you can show that the object that I'm describing here, so you specify some boundary conditions for these Euclidean metrics, it satisfies all the properties that you want of a thermal partition function. So for example, a first law, second law, zeroth law, smart relations, all relations that you could want are satisfied by this. And that's the subject of this famous paper of Gibbons and Hawking. So in other words, very natural, the Euclidean path integral in the semi-classical approximation of the bulk theory defines what you would call a partition function. And beta is a parameter, and it's basically just the parameter that enters into all the metrics that you're allowed to path integrate over. Well, more abstractly, what could we say? Well, we specify the boundary condition and we ask what are all the possible Euclidean solutions that asymptote to this boundary condition. So what are all the possible infilling solutions? This is where it gets interesting, because a natural generalization of this would be, well, I could just consider spacetimes in which I specify that the boundary has more components than one. So I could have any number of cycles, boundary cycles, beta 1 up to beta n. And then I define this object, z of beta 1 up to z of beta n, evaluated in gravity, as being precisely the same semi-classical path integral, but now the boundary condition is to have an n-component boundary. And this defines, in some sense, what I call here in inverted commas, a gravitational correlate of partition functions. Why? Because, well, that will be on the next slide, but I'm just showing here a graphical representation of the n equals to 2 case. So let us say that you have two cycles. Then the question is, what possible infilling geometries can I come up with? So what solutions are there to the Euclidean equations of motion of Einstein-Hilbert minus cosmological constant, which have two boundaries, but the bulk is completely arbitrary? Well, recently, this problem has actually been solved. And one has to say, as I will, really thanks to some wonderful work of Mirzakhani. In the end, this will go back to work of Mirzakhani. So in recent work, these three authors found that there are, among other contributions, there are two that I want to highlight. There is a disconnected contribution, which just looks like the product of the partition function at a given specified temperature. So this is like the solution that I drew before here at beta 1 times the solution at beta 2. And if I do this in particular in two-dimensional gravity, which I will get back to, we can actually also associate an Euler character with this. I'm just doing this for, as you know, for later use. This would be 2. But there are also connected contributions, which are not the Euclidean product of two individual boundary solutions, but they are actually solutions which have one and this. So these two boundaries are connected through one and the same infilling solution. And this is why we invoke this sort of science fiction term wormhole. In some sense, they connect two boundaries. But you know, don't worry, they have nothing to do with time travel or anything like this, because we're just talking about Euclidean connected solutions. So
yeah, So these are solutions of what equation?
I will show that in a second. So I'm here supposed to be talking about something that may be true in general dimensions, but there is one very concrete realization. In 2 dimensions, I will show you the equations. But the one thing that I want to point out before I go there is that this in some sense is disconnected because it's the product of 2 one-point correlates, whereas this thing means that there are also connected contributions, so that this Z beta 1, Z beta 2 does not actually factorize into 2 disconnected contributions because you have to take into account this correlate here. So one way of making this very concrete, there are, by the way, higher dimensional versions of this, but they're not nearly as well understood. And if you'd like, we can talk about it in the discussion. But one way of doing this very concretely and very explicitly is in what is known as Jakiv-Teitelbaum gravity, or JT, which is a 2-dimensional theory of gravity. So this theory has the classical action. So let's focus on this term. This is a 2-dimensional manifold. So I'm integrating d2x here. This is basically like Einstein-Hilbert with a negative cosmological constant here. So this would be r minus the cosmological constant. So the fact that it's plus means that that was negative. I also have an additional degree of freedom, which people call a dilaton, which is just a scalar field. And okay, I have this usual area density term here. This gets supplied with boundary terms to make the variation well defined. That's the standard thing in gravity whenever you have boundaries. But also, this dilaton has a tendency to asymptote to a constant. And if this is a constant, then actually root g times r plus 2 is just the Euler density, and its integral gives me the Euler number of whatever this manifold M is. So there will be some prefactor, which is essentially the constant value of phi times the Euler number. And so this is the classical action, and I'm formally considering the path integral over all possible 2-dimensional metrics that have specified boundary conditions. And in fact, this path integral can be evaluated thanks basically to the seminal work of Mirzakhani. And the reason why this works is that now if you have so this n correlation of boundaries, I'm now supposed to find all possible solutions to the Euclidean equations of motion of this theory here, which asymptote to n boundaries with specified lengths. And it turns out that these solutions can all be classified by essentially taking a genus G Riemann surface. So this exists at any genus, 2-dimensional solutions, Riemann surfaces. And for each boundary, I have a geodesic boundary in this Riemann surface. So this is a geodesic boundary, the red thing. In order to transform this into the asymptotic boundary of ADS here that I have specified, I glue in another specific solution of this theory, which is called, people call this a trumpet because sometimes it's drawn like a trumpet. And the actual path integral then reduces to a sum over all genus. Each genus is weighted by its Euler number, times an integral over the moduli space of Riemann surfaces that have n geodesic boundaries. So here I have just shown the example of 2 geodesic boundaries, genus 2. Okay, but in fact you have to sum over all geodesic boundaries, and you might want to have n of these asymptotic boundaries. And it turns out that the volumes of the moduli spaces that come in, they have been precise. These are precisely these Weil-Petersen volumes that Mirzakhani told us how to calculate using her wonderful recursion relation. So all this is to say that in this particular theory, those quantities can be explicitly evaluated, and they make contact to these geometrical objects. Now, the leading contribution, which is the one which has the lowest genus, that's because higher genuses will have this very large suppression factor because S0 is typically chosen to be a large parameter. So this comes from simply the guy which has no genus, and I'm gluing these 2 so-called trumpets. And that is the geometry which I had previously symbolized by this 2-boundary wormhole. Now, of course, in this case, this is not just words and pictures, it can actually be calculated. And well, you know, it's a somewhat technical thing. So I just wanted to show you what is the contribution to the spectral correlation function of this particular geometry. So this is, if you want, the first connected contribution. I also have the disconnected one, but the first connected one is this one. And it's basically 1 over the energy difference squared with some factors, and delta is the natural unit of energy. And this, for those of you who know about random matrix theory, this is the telltale sign of level repulsion, which is actually just another word another way of talking about this ramp and plateau phase. So if I take the Fourier transform of this object here, I get a linear rising spectral form factor. So this is, let me actually go back to it. This is precisely the reason why I was claiming that this region here and somewhat into this region, I can understand it by taking into account these so-called Euclidean wormholes. These come in as natural objects. Now, you get all sorts of corrections because we have all these higher genuses here, okay? And in actual fact, this is an infinite sum. And, you know, thanks to, again, Mirzakhani's wonderful work, and one should also say here, Hénin and Orantin, who have actually shown that this is the same recursion relation at what is known as the topological expansion of random matrix models. Very high order results are known, and actually this is really known in exquisite detail. But the most physically, the most interesting one really is this, the first contribution. So we have now basically shown that within this gravitational setup, there is the signature, the telltale signature of quantum chaotic level correlations, and it's encoded by this 2-boundary wormhole. So that is sort of a new entry, if you want, in this holographic dictionary, and it's really just a couple of years old by now. Now, okay, I'm really running out of time. So actually, what I wanted to show you is how this relates to quantum chaos. Let me think a little bit. I guess I can take until 5 minutes after the hour. Is that okay, or should I?
Yeah, sure, go ahead. Yeah, there were questions in between, so.
Okay, so let me just think about what am I going to, yes, okay. So what we did in recent years is we were indeed trying to show that, first of all, this makes sense, that these wormhole correlations are precisely the ones that you would expect also from a quantum ergodicity perspective. But we also wanted to formulate this in a way that it's not so specific to one particular theory. So this is, well, I started this work with Alex Altland, but other collaborators have also made major contributions since. So what we do is we basically calculate both on the boundary and in the bulk an object which is auxiliary, but actually turns out to be quite powerful. So we calculate a ratio of determinants over the Hilbert space. So H is the Hamiltonian of our system. And right now, let's leave it abstract, but of course, we might be thinking, for example, of this JT or its boundary description. And Z1, Z2, Z3, Z4 are sort of 4 energies that I can hold fixed. And the reason for calculating this object is that if I take twice the derivative with respect to any of these 2 energies, so dz1, dz2, for example, then I get the rho-rho correlation function. Essentially because the derivative of a determinant is the determinant times the trace of the inverse of this operator. And the trace of the inverse of this operator is what we would call the resolvent. And the resolvent is essentially it gives me the spectral density. But this object, the determinant, is in some sense a generating functional for these correlations of spectral densities. And it's a combination of objects that turns out to be mathematically very convenient, because we can use some tricks which come from the quantum ergodicity world due to Wigner and Yefetov, and we can actually formulate a quantum field theory of these determinants. And the way that we do it is, briefly, we basically integrate in degrees of freedom psi, So we explicitly write these determinants here as path integrals. And the kernel is then basically this operator here, or this constellation of operators. But what we then notice is that, in fact, the physics of this quantum field theory for small energy differences, that is for late times, because that's what we're interested in, is actually governed by a symmetry breaking principle. There is a symmetry which comes from the fact that these four Hamiltonians are all the Hamiltonian of the same physical theory. So this translates actually into a symmetry of these fields psi, which finally takes the form of a four-dimensional unitary symmetry. Now, for reasons that I have determinants in one of the determinants, these psi's are actually graded fields. So I have bosons and fermions, and so the symmetry ends up having to be graded. But in actual fact, there will be a mean field solution to this theory, which breaks that full symmetry in this pattern. So this U4 symmetry, two fermions, two bosons, is broken into two pairs of U2 symmetries, one boson, one fermion, one boson, one fermion. And this spontaneous symmetry breaking fully determines the low energy degrees of freedom. And the low energy degrees of freedom, luckily, are precisely the ones which govern the late time physics. So, the Goldstone theory of this symmetry breaking can be shown to reduce precisely to the physical content of random matrix theory. And well, one of the satisfying aspects of this is that it reproduces this random matrix theory physics for one specific Hamiltonian. So let's say, for example, this JT thing. Okay, but because it's this Goldstone, and you know, in our high energy community, we call this kind of thing an effective field theory. We like to refer to this as the effective field theory of quantum chaos. So the Goldstone physics can be actually shown to be given by a nonlinear sigma model on a coset that is determined by the symmetry breaking pattern. So the symmetry breaking pattern was U2/2 is broken to U1/1 times U1/1. And that defines the target space manifold of this sigma model. And well, turning the crank, because this really is standard, thanks to Callan, Coleman, Vess, and Zumino, we can actually extract these spectral correlations. This is not unlike the pion effective field theory in QCD, but let me not dwell on that comment, because the upshot I want to show is that this theory, so Alex Alton and I basically showed that it can be arranged into the same type of topological expansion as we have seen with JT gravity. And we can actually associate these individual terms with the individual terms that come out of this JT gravitational path integral. And so interestingly, it just turns out that the ergodic regime of these chaotic theories is described by what I call a topological theory of gravity. And each topology, so these are also Riemann surfaces for the R2 correlation function with two boundaries, but in general, you could have n boundaries. And it's a sum of a genus of the infilling geometries. And so, okay, there are two subtle points, but let me again not dwell on that. Each topology then predicts the coefficient of the leading singular term. So in other words, this term here, I can predict it from the symmetry breaking. And so if you do the calculation as we did, okay, it always has to be -1/2 s squared, where s is basically the difference of energy levels measured with respect to the average spacing between levels. So this, but you should think of this as omega squared in some natural units. And in all cases where people have found, or we have also found, these kind of have been able to identify these Euclidean two-boundary solutions in ADS-CFT, once you analyze it and put it in the right units, the term is precisely this one. It's -1/2 times s squared. It's always the same coefficient. And of course, from our effective field theory perspective, this must be the case because it's fully dictated by the symmetry. So this is another confirmation that this bulk wormhole gives the leading spectral correlation. So let me just summarize and take your questions, because I think I threw a lot of stuff at you, and I'm sure you might have clarifying questions. So I introduced this ADS-CFT duality, which is a mathematical laboratory to investigate gravity. And it somehow thinks, you can think of gravity as an emergent phenomenon, in the sense that you start with a theory which doesn't contain gravity explicitly, but you can still describe gravitational processes. The later stages of thermalization of black holes in this are tied to quantum chaos. And in particular, the level repulsion of eigenvalues of this quantum chaotic theory is encoded in Euclidean multi-boundary geometries. And again, if you like the science fiction term, one can call them wormholes. So now, here more specifically, so we actually can do more than just this leading singularity. We can actually, really map out the entire curve that I showed you. But for reasons of time, I couldn't go into all these details. And we also identify some simple geometric principle, namely this coset space sigma model. And okay, one can go beyond the unitary class. I implicitly only showed to you what happens in the unitary class, but all the other classes work as well, and you just have different cosets. In fact, all the symmetric cosets classified by Cartan are allowed. And so, okay, let me just say open questions. So really, how do we phrase in a conceptually understandable way this causal symmetry in the bulk? But I think the most interesting one, let me just end on that remark, is this one here. How do we understand, so let me paraphrase, how do we understand this structure, this EFT of symmetry breaking that gives rise to these level correlations in a geometric way in higher dimensions? We somehow understand this thanks to Mirzakhani and to Saad Shankar and Stanford in 2 dimensions very well, but in higher dimensions, we only have glimpses, namely some diagrams that work, but the general story really hasn't been fleshed out yet. And I would very much like to do this. So thank you for your attention, and I'll be happy to take your questions.
Thank you, Julian. Thank you for this very nice talk. The floor is open for questions, so please go ahead. So you can just unmute yourself and ask a question. So let me start maybe with something very general. So you said that some people are working on Lorentzian versions of things. So how does this, how would that translate? So could I do everything you said Lorentzian, and what would be then the correspondence? So would you take, topology plays an important role in your things. So would you think about those various topologies as topologies of, say, Cauchy surface in sort of, 2+1, or how would I use these results in Lorentzian?
Yeah, that's a very good question. So my remark there was people that would like to prove ADS-CFT more generally, they are working on basically mapping correlation functions in Lorentzian. And so they are still in principle working at genus 0. And so they're not really talking about these kind of results, but it is true that you can think of these solutions, these kind of solutions here, you can think of them also in Lorentzian. Again, the one that is at genus 0 is relatively simple. This turns out to be some geometry that is related to periodic identifications of known Lorentzian geometries. The higher genus ones, I'm not aware of any concrete constructions, but I agree with you that it presumably would have the spatial part of it. So if you look at some Cauchy surface, then that would have non-trivial topology.
Right, yeah.
But it's not clear to me that you would be able to find non-singular Lorentzian geometries that way. But I think it's a nice question. So there's 2 aspects of it. One is the general aspect, that people that think very generally about ADS-CFT, they typically think about Lorentzian signature and use Euclidean results just as a technical tool. In this particular thing here, where we talked about higher topology, so far only Euclidean results are really under any kind of control. But the question that you pose, I think, is a very important one.
Okay, thank you. Yeah, so yeah, that clarifies. Thanks a lot. Are there any more questions?
I have a question. What about supersymmetry? Did it play any role in your talk?
None whatsoever, except in a very surprising way. This theory here is one that has no supersymmetry. So this is just a bosonic theory. So from the gravity perspective, supersymmetry did not play a role. However, this sigma model that I constructed actually has hidden within it some supersymmetric structure. But I'm actually not suggesting, by the way, that this has to do with supergravity. This is actually something that in general, in this approach to quantum chaos comes out. So this was actually pointed out by Yefetov. Okay. He worked actually on these kind of constructions in mesoscopic physics. And what is actually the case is that this symmetry here, the one we call causal symmetry, I did not really explain well why we call it causal symmetry, but let's put it to a side for a second. This is actually a graded symmetry. And if you want, high energy physicists would probably call this a supersymmetry. And in particular, this supersymmetry comes out, why? Because of the way that I define this observable. I basically have determinants in the numerator and the denominator. And if I set these energies equal in pairs, then, well, they would cancel. And that is essentially a property of supersymmetric theories. And so the fact that if I set the energies equal in pairs and they cancel leads to some interesting symmetry constraints on this field theory that we have here. And I believe that those are in some sense related to, indeed, to supersymmetry. Yeah. But it's not, yeah, the underlying theory, which is described by this Hamiltonian here, need not be supersymmetric.
And this is a Hamiltonian of a two-dimensional theory, or?
Yeah, so in fact, you could think of it as a Hamiltonian of a two-dimensional theory, but this general approach is a general approach. So I could put in any Hamiltonian of a quantum system that has an ADS-CFT dual in our context. And so in particular, the one that is most well known is actually a four-dimensional theory. This is this, well, in this case, by the way, it would be supersymmetric. It's the Super-Yang-Mills theory. You could actually think about developing this effective field theory for Super-Yang-Mills theory, and then those would be Hamiltonian of Super-Yang-Mills. But I was thinking more about lower dimensions. So this would, for example, be a two-dimensional CFT, or something like this, the dual of JT, etc. I don't know if I said this very well. I mean, right? The idea is that you give me some well-defined quantum theory. It could be a quantum field theory, for example. Let's say QCD. And you could ask the question, are there correlations in the spectrum of QCD that, for example, have to do with level repulsion? And one way of trying to answer that question is to subject QCD to this framework of thinking about quantum chaos. In this case, the Hamiltonian that's in here, you would try and put something like the QCD Hamiltonian in here. Of course, doing this in practice is, you know, I think extremely difficult and certainly beyond my capacities.
Thank you. Martin, would you like to?
Yeah, I don't have a question. I just wanted to add a comment.
Yes.
I do appreciate your effort to simplify things for a rather general audience. But there's one detail which is kind of dear to me that I like to add as a comment, namely that the symmetry group is actually non-compact.
Yes,
U2/2, but
yes.
Obviously, since you worked with Alex, you're aware that the left 2, there's a signature, and it is U1, 1. And so that's well known. This was the contribution of Wegener, and it was appreciated by Yefetov and I think by everybody following. One thing that is not sufficiently appreciated, and I believe it will come to relevance in the further development of your story, is that in a non-compact Lie algebra, you have different types of orbit. So when people say that the symmetry determines everything, that just by knowing the symmetry, you know the sigma model, and therefore you know all of the late time physics and the restoration of causal symmetry, that, if you ask me, is too optimistic. This requires, in order for that standard scenario to be borne out, requires a proof that you actually renormalize to the standard orbit. But there are other orbits around. In my recent work, I found a situation where the theory actually goes to a different orbit in the non-compact, in the Lie algebra of the non-compact group. So I'm trying to get heard. Alex doesn't want to listen. I hope that some other people will start listening. So I think I have something to say, and it's related to this. Well, so I think it's not the point of your talk here. You're trying to communicate a very big story, a fantastic thing to a audience that's looking at a distance. So, but at the end, since nobody else is asking questions anymore, I decided I'm going to speak up and add this little comment. So thank you.
No, well taken. And actually, I would be interested in hearing more about it. I mean, okay, so you could start by sending me an email about the most concise paper about this, but I might call you and ask more questions. But I mean, concretely, since we're now on this slides, Martin is of course absolutely correct that I should have written U1,1/2. But he was also correct that I did not do this because, well, I didn't want to go into too many details. I already probably overloaded in some sense. Yeah.
Okay, thanks for the comment. All right. Any more questions, comments, remarks? That does not seem to be the case. So let's thank our speaker again for this very nice talk and explain